Welcome to this session on refraction at a plane surface. In this session we will be discussing the following aspects. Refraction of light, we will define the phenomena of refraction. We will look at laws of refraction and relative and absolute refractive index. And then the concept of refractive index in terms of velocities and wavelength. Invariance of n sine theta. Refraction through parallel sided glass slab. Expression for lateral shift. We'll also look at the concept of apparent depth, which is meant, and related to that we have the concept of normal shift. And then we look at the very important concept here of total internal reflection and its applications. So these are the topics we'll be covering here. To start with, I want to mention here that there are certain materials, optical media such as glass, in which light travels with the same speed in all directions. So light travels with the same speed in all directions in certain optical media. Such optical media are called as isotropic materials. So isotropic materials are those materials in which light travels with the same velocity in all directions. For example, glass. Glass is an isotropic material. Now in our discussion we are limiting to only isotropic materials. So the discussion we are going to have here regarding the refractive index or invariance of n sine theta, etc. are all meaningful only for isotropic materials. There are other materials called anisotropic materials which are generally crystalline. For example, quartz. Those materials do not show these characteristics or these functions that we are discussing in this session. So our discussions are restricted only to isotropic materials such as glass. So with this brief introduction, now let us start off with the concept of refraction of light. So if I take a plane surface of glass here, a slab of glass for that matter, and then I have light incident on this. I have an incident ray of light falling on the surface. We know from our earlier discussions that part of the light gets reflected. We talked about the phenomena of reflection earlier. So part of the light gets reflected, and we know that the angle of reflection and the angle of incidence are the same when we talked about reflection. Now if you are taking transparent materials such as glass, what happens is part of the light gets reflected, a very small part of the light gets reflected, but a majority of the light waves get transmitted in this media. Majority of the light gets transmitted in this media. This is medium 1, which generally is air, medium 1. This will be my medium 2. This is optical medium 2, this is optical medium 1. So this is the incident ray. It falls on this medium 2, is incident on this medium 2, and it travels through this medium. Now there is a difference in velocity of light in this medium compared to this medium. I mean, the velocity of lights are different here and it's different in this medium. Because of these differences in velocity of light when it travels in medium 2 bends. Either it bends towards the normal or away from the normal. This deviation or change in direction of light when it travels from one medium to another medium is known as refraction of light. So refraction, the bending or deviation of incident ray of light when light travels from one medium to the other is called refraction. So refraction is a phenomenon in which the light ray gets deviated or bends when it travels from one medium to the other medium. This happens at the point of incidence. This is the point of incidence. So that's the definition of refraction. There are certain other interesting aspects here when we look at the phenomena of refraction. Now, the laws of refraction state certain things. One is the incident ray, the refracted ray and the normal, they all lie in the same plane. That's one of the observations that have been made over the years. So this is the incident ray, this is the normal, and this is the refracted ray. So the ray of light, that the deviated ray of light that travels in medium 2 is called a refracted ray. This is the incident ray, this is the refracted ray, this is the normal at the point of incidence. This is the point of incidence where the incident ray is touching the medium 2. So OMN, OR, OI. So in this case, OI is the incident ray, MON is the normal at the point of incidence O, OR is the refracted ray. OR is the refracted ray. So the laws of refraction, let me state the laws of refraction here. Laws of refraction. We have two laws of refraction. The first law of refraction states the incident ray, the refracted ray, and the normal at the point of incidence, all lie in the same plane. And now there is the second law of refraction. It says that the ratio of the angle of incidence to the angle of refraction is constant. So if I were to call this as I, this is the angle of incidence. That is the angle the incident ray makes with the normal is called the angle of incidence. So if this is the angle of incidence and this is the angle of refraction, then the second law of refraction states that the angle of it's not the angle that is constant, it says the sine of this angle, the ratio of the sines of this angle is constant. So it says that the ratio of sine of angle of incidence to sine of angle of refraction is a constant. For a given pair of media, optical media, and for the given length of wavelength, of course. So the ratio of the sine of the angle of incidence to the sine of angle of refraction is a constant for a given pair of media. That means if I consider air and glass, for example, sin I divided by sin R is always a constant. So let me write it down here in terms of a formula. That means therefore I have sin I by sin R equal to constant. So I say sin I divided by sin r is a constant. This equation is also known as Snell's law. Or the sine law. So this law was enunciated by Snell, the scientist by name Snell. So in honor of this scientist, this equation is called as Snell's law. That is, the ratio of sine of angle of incidence to sine of angle of refraction is a constant for a given pair of media. Sin I divided by sin r is constant, is also known as Snell's law or sine law. So let me recap this again quickly. So it says that the first law of refraction says that the incident ray, the refracted ray and the normal at the point of incidence, they all lie in the same plane. What it means is, if I consider this board as the plane, then if this incident ray lies here, this normal is lying here, this ray OR has to be on this board, on the plane of this board. I cannot have this incident ray here and I cannot have the refracted ray coming out in this direction. That is not permissible as per the law. The law says that if this is the angle of incidence, this is the normal, this is the refracted ray and it lies on this same plane. So all three lines lie on the same plane. The next law says that the ratio of sine of incidence, which is I here, that is the angle between the incident ray and the normal at the point of incidence, that is sin I, the ratio of sin I divided by sin r is a constant for a given pair of material, medium 1 and medium 2. So these are the two laws of refraction, and then sin I by sin r is a constant, is also known as Snell's law or sine law. So with this we have looked at refraction of light, definition of refraction and laws of refraction. Let us move on to the next topic of relative and absolute refraction index. So let us discuss about relative and absolute refractive index. So that means, so just now we mentioned from the second law of refraction, now we are talking about relative and absolute refractive index. So let me write down here relative and absolute refractive index. So just now we mentioned from Snell's law we have from Snell's law or the second law of refraction, we know that sin I by sin r equal to constant. We call this constant as 1 and 2. If we designate the constants as 1 and 2, then 1 and 2, or let's say 1 and 2 is equal to sin I by sin r. 1 and 2 is the relative refractive index. We call 1 and 2 as a relative refractive index. So from Snell's law we know sin I by sin r is a constant. We call that constant as 1 and 2, or 1 and 2 equal to sin I by sin r, which is a constant. So we call 1 and 2 as a relative refractive index between medium 1 and medium 2. So it's a relative index because we are comparing two media here. Now if medium 1 is air, medium 1 is air or vacuum, then we have n is equal to sin I by sin r, In this case we call n is the absolute index, absolute refractive index. So if we are having two different media and this medium are not air, then we have the relative refractive index. However, if medium 1 turns out to be air or vacuum, then the index that we get here, the constant ratio that we get here between sin A by sin R is a constant, and that constant is called the absolute refractive index of medium 2. So this is the absolute refractive index for medium 2. So if I have air here, and if I have a glass, and if I measure sin A by sin R, then the value that I get for sin A by sin R is the absolute refractive index of glass. That is what we mean by this. So the absolute refractive index is given by the ratio sin A by sin R, and where medium 1 is air or vacuum. That is about the difference between relative refractive index and absolute refractive index. Now we can state this refractive index in terms of velocities and wavelength. So if we have to state it in terms of velocities, then so refractive index in terms of velocity. Let us consider this first. From wave theory of light, it is shown that from wave theory of light, it can be shown that 1 and 2 is equal to velocity v2 divided by velocity v1. 1 and 2 equal to v1 divided by v2. This refraction of light, the phenomena of refraction of light, is due to the difference in velocity of light in medium 1 and medium 2. That is the reason we get this refraction. Now refractive index in terms of velocity, if I know the velocity of light in medium 1 and if I know the velocity of light in medium 2, I can find the refractive index of medium 2. So from wave theory of light, it is known that 1 and 2 is the same as what we got here, is equal to v1 divided by v2, where v1 is the velocity of light in medium 1 and v2 is the velocity of light in medium 2. So this is a v1 by v2. Now from this expression we can get the value for absolute refractive index. Now let us say this value is air, if this medium is air and this is glass, in which case I have, if medium 1 is air, then we have n, the absolute refractive index of this medium 2 is given by c divided by v2, where c is the velocity of light in air or vacuum, which is 3 into 10 to the power of 8 meters per second. So I can get the absolute refractive index of a medium by this expression. Here v2 is the velocity of light in medium 2. Now likewise, I can extend this logic and say refractive index of light in terms of, so again in terms of wavelength, it can be shown that 1 and 2 is equal to lambda 1 divided by lambda 2. In terms of wavelength, it can be shown that 1 and 2, the refractive index is equal to lambda 1 divided by lambda 2, where lambda 1 is the wavelength of light in medium 1 and lambda 2 is the wavelength of light in medium 2. So I can state the refractive index, the relative, where we discussed about relative refractive index, where we said 1 and 2 equal to sin A by sin R. From this we said that if medium 1 is air or vacuum, then the value of n that I get corresponds to the absolute refractive index of medium 2. So that is why I get n equal to sin A by sin R, where n is the absolute refractive index and medium 1 is air. Then when we express refractive index in terms of velocity, from the wave theory of light we know that 1 and 2 is the same as v1 divided by v2, where v1 is the velocity of light in medium 1, v2 is the velocity of light in medium 2. So if medium 1 happens to be air or vacuum, then I know that the velocity of light in air or vacuum is c, which is 3 into 10 to the power of 8 meters per second, and therefore in medium, if medium 1 is air, I have the absolute refractive index of medium 2, which will be c divided by v2, where v2 is the velocity of light in medium 2. Now I can also express the refractive index in terms of wavelength of light in medium 1 and medium 2, and if I do that, I get in terms of wavelength 1 and 2 is equal to lambda 1 divided by lambda 2, where lambda 1 is the wavelength of light in medium 1 and lambda 2 is the wavelength of light in medium 2. So that is about the refractive refraction, the phenomena of refraction, the laws of refraction, the concept of relative and absolute refractive index, and then refractive index in terms of velocity, refractive index expressed in terms of wavelength of light. Now let us find a correlation between refractive index and absolute refractive index. So we are now going to derive an expression between relative refractive index and absolute refractive index. So I'll erase this portion. So we derive an expression for relation between relative refractive index and absolute refractive index. So we're going to find the relationship between relative refractive index and absolute refractive index. We know that by definition, we know that 1 and 2 is equal to V1 divided by V2. We also know that we also have N1, that is the absolute refractive index of medium 1, is given by C divided by V1, where V1 is the velocity of light in medium 1, optical medium 1. We also have N1 equal to this one, and N2 is equal to C divided by V2. So we have this expression N1 and 2 is equal to V1 by V2, and we also know that N1, the absolute refractive index for medium 1, is C divided by V1, where V1 is the velocity of light in medium 1, and N2 is equal to C divided by V2. So from these three expressions we can find the relationship between the relative refractive index and the absolute refractive indices. So the way we do is, let me find out the value for N2 by N1. Therefore N2 by N1 is equal to, if I call this as equation 1 and I call this as equation 2, from equation 1 and 2, I find N2 divided by N1 is equal to C divided by V2 divided by C divided by V1, which is the same as C divided by V2 multiplied by V1 divided by C. I cancel off C here, and therefore I get N2 divided by N1 is equal to V1 divided by V2. So from, I call this as equation 3. From equations A and 3, I get 1 and 2 is the same as V1 by V2. I substitute V1 by V2 with N2 by N1, you get N2 by N1. So this is the expression that gives me the relationship between relative refractive index and the absolute refractive index of the two media. So 1 N2 is equal to N2 divided by N1. So in other words, the relative refractive index of media 2 with respect to media 1 is the same as absolute refractive index of media 2 divided by absolute refractive index of media 1. So with this we are concluding the discussion on refractive index in terms of wavelength and velocity. We have covered up to this place. Now we look at the concept of invariance of sine theta, and then we will move on to the next topic, refraction through parallel sided glass slab, which is also called as lateral shift. So I will erase this portion, then we will work on the other topics. Okay, let me retain this diagram for the time being. Let us now look at the concept of invariance of sine theta. We are looking at this aspect now. So we know that from Snell's law, we know that 1 and 2, there is a refractive index. There is a relative refractive index is given by sin I by sin R. If I were to refer to this diagram, it is sin I by sin R. And call that as equation 1. We also know, this is what we just discussed just some time back when we were talking about the relationship between absolute refractive index and relative refractive index. So from that equation we know that 1 N2 is equal to N2 by N1, where N2 is the absolute refractive index of medium 2 and N1 is the absolute refractive index in media 1. So this is equation 2. If I observe these two equations, I have 1 N2 as a common here. So 1 N2 is N2 divided by N1, which is the same as sin I by sin R. If I cross multiply this, I get N2 into sin R is equal to N1 into sin I. So this equation shows that N sin theta in general is invariant. That means it is a constant. For example, if I were to make light travel from this glass slab back to again air, then this would be a ray of light, and then when it gets reflected, this is the normal. This would be the angle of refraction again here R. So this would mean that in this case this would mean that N1, which is the absolute refractive index of media 1, N1 into sin I, N1 into sin I is the same as N2, which is absolute refractive index for medium 2, into sin R. That's what I am getting here. Which means that N sin theta is invariant. So for any given media, when light passes from one media to other media, N sin theta is invariant. So in this case, N1 sin I, N1 absolute refractive index in medium 1 multiplied by sin I is the same as absolute refractive index in medium 2, that is N2 multiplied by sin R. So which means that N sin theta is invariant or is a constant. So with this we have covered this aspect of invariance of N sin theta. We will now move on to the next topic, that is about the lateral shift. Let us now discuss about refraction through parallel sided glass slab. We will also derive an expression for what is known as lateral shift. So consider this diagram wherein ABCD represents the glass slab of thickness T. Note that I mentioned here T is the thickness of the glass slab. Effectively T is equal to AC. Now PQ is an incident radiation, and as we discussed earlier, because of refraction of light, this light, the ray of light inside this medium gets deviated from the straight path. So it bends towards a normal and then it travels this distance, and when it comes to the incident point here at R, the light gets refracted again, because light is moving from a denser medium to a rarer medium here. From medium 2 to medium 1. The light of the ray is moving from medium 2 to medium 1 again, and therefore the light gets refracted once again at R. So this is the ray of light that is emerging from the glass slab. So RS is the emergent ray. We call RS as the emergent ray. PQ is the incident ray. QR is the refracted ray. Now we know that T is the thickness of the glass slab. Let us find out about RS, much more about RS. Now here we have noticed experimental results have shown that there is a lateral shift. There is a lateral shift in the rays that are emerging out from here. That means if I take a glass slab, and if I make light incident on that, the emergent ray is not coming out in the same direction, but it comes out in a direction that is laterally shifted. For example, if this is the glass slab and if I make a ray emergent here, now assuming that I didn't have this glass slab, the ray of light would have emerged here, but because of my keeping a glass slab and because of the incident ray passing through the glass slab, I find that the rays emerging are in this direction. It is parallel to the incident ray, but it is laterally shifted. That means this path is shifted, and then I find the rays coming out from this point onwards. So that is what we mean by lateral shifting. This is the incident ray, it gets laterally shifted. And that's what is depicted in this diagram here. So this is the incident ray. The incident ray would have been PQY, but because of this glass slab being placed there and because of the refraction process, the light takes a path PQ, R and then S. So RS is laterally shifted from TY. So we define lateral shift as perpendicular distance. This is the perpendicular distance RT between emergent ray, RS is the emergent ray, and incident ray. So this is the lateral shift. Now here we will try to find an expression for the lateral shift. So first let us find out whether RS is parallel to PY. So here, that's what I am trying to do here. And we are using the concept which we discussed just now, that invariance of n sine theta, which meant that in any media the refractive index of this media multiplied by sine of this angle is constant, and therefore when I apply that principle to Q, to the point Q, at Q, I find that 1 into sine I, because refractive index of air is 1, so 1 into sine I, which is I is the incident angle of incidence, 1 into sine I is the same as n, that is the absolute refractive index of glass, n into sine R, because R is an angle here. So 1 into sine I equal to n sine R. I call that as equation 1. Now I apply that concept to point R here, this point R. So here I find n is the refractive index of medium 2, or glass here. So n into sine r, this is angle of incidence now. You notice that this line is parallel to this line. This is normal. This line is parallel to this line, and since this angle is r, this angle is r, and therefore I find that sine n into sine r at this point is the same as 1 into sine I dash. Sine I dash, where I dash is the angle between the emergent ray and the normal at this point r. So from equations 1 and 2, I find that 1 into sine I is equal to n sine r, and n sine r is the same as 1 into sine I dash. Therefore 1 into sine I equal to 1 into sine I dash, or sine I is equal to sine I dash, which also means that I is equal to I dash. That means this angle of incidence is the same as this angle I dash, which also implies that RS is parallel to PQTY. PQTY is parallel to RS. That means the emergent ray is parallel to the incident ray. Emergent ray is parallel to the incident ray, and the perpendicular distance between these two rays is what is called as a lateral shift. We will now calculate the value for the lateral shift. So let me calculate the value for lateral shift. That means we need to calculate the distance RT. We need to find out the value for RT. Now for us to find out RT, we know this angle, we don't know this distance. So let us try to evaluate the value for this hypotenuse here, QR. Let us find the value for QR. To find the value for QR, we consider triangle QMR. So in triangle QMR, angle Q is R. And now this distance QM is T, which is the thickness of the slab. And therefore I have adjacent side and I know the angle here. And this is a right angle triangle. QMR is a right angle triangle, and therefore the hypotenuse QR can be evaluated. Now let me find out cos of R is adjacent side divided by hypotenuse. So I have cos of angle R is equal to adjacent side QM divided by hypotenuse QR, which is the same as QM is AC, which is the same as T, that is the thickness of the slab, divided by QR. So this is the expression I get. So I know the value for QR now. Therefore QR is equal to T divided by cos R. This is equation 1. Now I know the value for QR. I need to find out the value for RT. Note that this is a right angle triangle. QRT is a right angle triangle because this is P or RT, because RT is perpendicular to PQT and Y. PQTY. RT is perpendicular to PQTY and RS is parallel to TY. So therefore RT is perpendicular to PQTRY, which means QRT is a right angle triangle for me. QRT is a right angle triangle, and this angle Q, RQT, we have also RQT in triangle RQT angle RQT is equal to this angle is the same as this angle. So that means MQT is I, out of which MQR is R, and therefore I know that RQT is equal to I minus R. I minus R. So this angle is equal to I minus R. So I know that this angle is equal to I minus R. I know the value for hypotenuse here, so I can calculate the value for RT. So if I know this angle, then I find this, so I use sine theta, which is sine of, therefore I have sine of I minus r, which is this angle, is equal to opposite side RT divided by hypotenuse, which is QR, which is the same as RT divided by QR is T divided by cos R. Therefore, this is equal to T into cos R. So I have sine I minus R is equal to RT divided by T into cos R. Our aim is to find the value for RT, which is the lateral shift. So I will erase this much in the board and then continue from this expression onwards. So therefore I have, from here I have sine of I minus R is equal to RT divided by T into cos R. Therefore I have, I want to find the value for RT, so let me get RT. Therefore RT is equal to T into sine of I minus R divided by cos R. Or RT is equal to T minus T divided by cos R into sine I minus R. This is the expression for the lateral shift. This is the expression for lateral shift. So what I did was I found out this distance, this value QR, by considering this triangle MQR. I know this is R and this thickness of this slab is T, so I was able to evaluate the value for QR. Next I consider the triangle RQT. I know the angle Q here, angle RQT, which is I minus R, because this value is I, that is MQT is I, and then MQR is R, and therefore I know that RQT is equal to I minus R. So in this triangle I know the value for QR, I know this angle, I can find out the opposite side, and therefore I found out the value of RT, which turns out to be T, the thickness of the material, divided by cos R, cos of this angle, multiplied by sine into I minus R. So let us take a specific example. If I is equal to 0, that means this is the angle of incidence. There is a ray of light falling here. Will there be any lateral shift? Let us try to find out from this expression. It is noticed that for angle of incidence I equal to 0, there is no lateral shift. The ray travels straight down this path. And therefore, for one of the notings we have here is the lateral shift is 0 when the angle of incidence is 0. When the ray of light is passing through the normal, the lateral shift is not seen. And we also know that the lateral shift is dependent on the thickness of the material, or the thickness of the glass slab. So larger the value for this T, larger will be the lateral shift. So these are some of the considerations that we can think of. So with this we are concluding the discussion on refraction through parallel sided glass slab. Let us now move on to the next topic, that is about normal shift. I hope this aspect is clear. So RT is equal to T divided by cos R into sine I minus R. Let us move on to the next topic, that is that is normal shift. So let us look at the aspect of normal shift. We are here for apparent depth. Now consider a situation, consider a case where we have a denser medium here and we are observing an object O which is in the denser medium from the rarer medium. That means we are in the rarer medium, we are observing an object that is kept in the denser medium. So what happens in this case is the object O, the rays from object O reach the surface here and then they get refracted at this point. So the rays gets refracted from this point, so we get a narrow divergent beam of light. So assuming we are observing close from the normal, that is we are observing this object close from this normal. So although we don't see a single emergent light there, we see a divergent rays coming out here. So this observation point for our eye is close to this normal. So what happens is actually although the rays are emerging from O in this case, since because of this refraction the lights get the rays of light get refracted at this point. So if we extend these rays backward, we will find that the image is at I. That means our eyes perceive as if the image is at I. Although the object is at O, we think that the object is at I. So this is, I is called the image. So I is called the image here. I is the image. Or the virtual image rather. I is the virtual image because the image does not exist at point I, but we feel as if the object is at I. So I is called the virtual image. This phenomena is known as normal refraction. So the object O, although it is at this location, appears to us as if it is at location I because of the process of refraction, and this phenomena is known as normal refraction because we are observing closer to the normal. So that process is known as normal refraction, and obviously there is an apparent shift in location of this object from O to I. That means we think that the object is at this location I because that is the virtual image that is formed. So this shift in location is what is known as a normal shift. So the apparent shift in the position, so let me write it down there. So the apparent shift in the position of the object along the normal, this is the normal, along the normal is called normal shift. So this is the reason that we find that objects, although they are much deeper in the liquid here or water for example, we find as if they are at a higher elevated point. So it is because of this property. So because there is an apparent shift in the position of the object along the normal and because of the normal shift. So I hope this concept is clear. with this concept in mind, now let us find a expression that will give us the normal shift, that will give us the value for normal shift. So let me draw a diagram wherein I will amplify this diagram and then we will work out an expression for normal shift. Let us now look at normal shift. We will derive an expression for normal shift. Essentially what we have to do is, as we mentioned earlier, normal shift is OI. Consider this case of a glass slab. We are observing from this end, which is close to the normal. The depth of this glass slab is T, the object is at O, and we see the virtual image at I. So we need to find out the value for expression for OI, which is the normal shift. So carefully look at this diagram. So we are watching it from here, which is the rarer medium, this is the denser medium, then we have the object at O, and then the angle of incidence is I here. When it gets refracted, the angle of refraction is R. We are observing from this end. As we mentioned earlier, if we extend this ray backward, then we'll find that it meets this normal at a point I, which is the place where I have the virtual image. So I know that AC or PO for that matter is T, which is the depth of the glass slab here. So our aim is to find OI. So let us consider from the figure, I know that this angle is I and this angle is R. Let me consider this, let me consider POR and ORN. I know this is I and therefore this angle has to be I. Therefore POR is I because of alternate angles, and therefore I have POR is the same as ORN, which is equal to I, because this line and this line are parallel to one another and OR is passing through this parallel line. And likewise I have PIR. If I look at PIR and then MRS, I am looking at MRS and PIR. Since this angle is R, I find this angle to be R because of corresponding angles. These are corresponding angles. So PIR and MRS are corresponding angles, and therefore I know the value for R. I know the value is R here, and I know that the value here is I. Angle is I. Now let me find out from this triangle POR, from triangle POR, which is basically a right angle triangle. Triangle POR, sin I is equal to opposite side divided by hypotenuse. That means sin I is equal to PR divided by OR. Sin I is equal to PR divided by OR. And then in triangle, from triangle PIR, from triangle PIR, I have sin R is equal to opposite side PR divided by hypotenuse IR. Sin R is equal to opposite side is PR divided by IR. I have these two equations. So dividing sin I by sin R, 1 by 2, I get sin I by sin R. Sin I by sin R is equal to PR divided by OR. PR divided by OR multiplied by sin R is PR divided by IR, PR into IR. So PR gets cancelled with PR. So therefore I have sin I divided by sin R is given by IR divided by OR. So sin I divided by sin R is equal to IR divided by OR. And since R is close to P, we have sin I by sin R. Sin R is equal to IR can be approximately equated to IP, and then OR can be approximated to OP. So this is the equation I have now. Now again from Snell's law, I know that N2, if N2 is the refractive index, N2 is the refractive index here of this medium and N1 is the refractive index of air, then I have N2 into sin I. N2 sin I is the same as N1 sin R. And since N1 is equal to, N1, the refractive index of air is equal to 1 and N2 is equal to N. I'm considering the absolute refractive index of this medium to be N. Then we have N2 sin I will become N sin I is the same as sin R, because N1 is 1. That means sin I by sin R, or I can write this as N is equal to sin R by sin I, which is the same as, so N is sin R divided by sin I, which is the same as OP by IR. OP by IR. This is from equation 3. From equation 3. This is quite interesting because I find the refractive index in terms of OP by IR. OP by IR is approximated to IP, so I should have had IP here. So I have IP here, so this should be, sorry about that, let me correct that. So I've written down the steps here. So note that since R is close to P, I should have sin I by sin R given by OP divided by IP. OP divided by IP. And next, from Snell's law, I find that N2 sin I equal to N1 sin R, and since N1 equal to 1, index for air is 1 and N2 is equal to N, I am calling that as N, I have N sin I is equal to sin R. And therefore I have N is equal to sin R by sin I, or N is the same as OP divided by IP. Notice that we find sin I by sin R equal to OP divided by IP, and now I find refractive index of this medium is the same as OP divided by IP. Now our aim is to find OI, which is the OI, which is the apparent, which is the normal shift. And therefore what we do is, here we consider Sn, we designate this OI as Sn, there is a normal shift. Normal shift is equal to OI, which is the same as OP minus IP. Notice that OI is the same as OP minus PI. So OP has a value T. So therefore I have OP minus PI is equal to OP minus I express IP in terms of the refractive index. Therefore I find Sn is equal to OP minus IP as the same as OP minus OP divided by N, where N is a refractive index. Or if I simplify that or replace T for OP, I find that Sn is equal to T into 1 minus 1 divided by N, where N is a refractive index. There are a couple of observations that you need to make here, and that is the normal shift. The normal shift is dependent on the thickness of this material. So the normal shift is dependent on the thickness of this material and is also dependent on the refractive index of this medium. So these are couple of observations that you need to remember. So Sn is equal to, this is the normal shift, expression for normal shift is T, which is the depth of this or the thickness of this multiplied by 1 minus 1 divided by n, where n is the refractive index of this medium. With this we have completed our discussion on normal shift. Next we will take up total internal reflection and its applications. Thank you.